This is Component 3 mock and paper A1. Question 5. And here we've got a model artificial gut that somebody's built. And it seems to have all the sections that you might recognise, and they're putting in food at one end, and in various places they can stop and start the process and put enzymes in and adjust the pH and things like that. And at any point in this they can take samples out and see what they've got. Where does this end? You'd think the end would be the anus or wherever, but actually it says to large intestine. So this is actually only part of the model. The large intestine is down here somewhere. So you think, right, does this tie in with what I know? So food goes into a stomach, and then there's some more sections before the large intestine. So this is the duodenum, and then the ileum, the start of the ileum, and then the end of the ileum, and then eventually to the large intestine. I can think about enzymes being put into the stomach and enzymes being put into the duodenum. So enzyme pump B might be the pancreas or something like that, maybe. What about saliva? Well, there's actually no mouth on it, so the mouth is actually up here, and kind of saliva and that sort of thing. So actually the mouth, buccal cavity, and the large intestine are actually not shown on this diagram. So if your answer's going to be to do with those, it's probably not going to be right. Part A1, name the likely enzyme. If it says name something, it wants the name, not the family of enzymes or anything else about it. It wants the name. And pump A pumps an enzyme into the stomach. The name of the enzyme that you know goes into the stomach is pepsin. Or you could have possibly put its precursor, pepsinogen. So you could have put pepsinogen, which gets activated. So if you said protease, it's kind of right, but that's not the name of it. There's so many different proteases. And again, name the likely protease added by pump B. So if you said endo or exopeptidases and things like that, it's heading in the right direction, but it wants its name, and its name that's put in by the kind of pancreatic juice into the duodenum. That is trypsin. Or indeed you could have said its kind of precursor, trypsinogen. That's the actual name of the specific enzyme. The pH of the stomach is acid, whilst at region C is alkaline. So we've gone from acid to alkaline conditions. How is this pH change achieved in the real human gut? So what happens to change it? Yes, you can say it neutralizes it and so on. Yes, that's your kind of year 7 pH scale. But what actually happens? And so we want to know, where does this kind of alkali come from? And we can say that the pancreatic juice, or the bile, those juices are alkaline, and that's what passes into the duodenum. So the juice, for example, bile is alkaline, and this passes into the duodenum, and it's because it contains bicarbonate, and so the alkali is bicarbonate. And here it doesn't actually mention Brunner's glands secreting alkaline kind of mucus. It's not on the mark scheme, but we'd probably accept It doesn't say about just the secretions. In real human gut, we might talk about Brunner's glands and secretions as well. Give the main function of C and D. So the main function of C and D. Okay. The most common error here is to confuse D with the large intestine, whereas, as we said before, large intestine isn't even on this diagram. So the two parts of this small intestine, the kind of duodenum, and what's the main thing going on there with enzymes being squirted into it, and D, where there doesn't seem to be any enzymes being squirted in, but it must have some other function. So C, with these enzymes, that's going to be digestion. And it really wanted that word. If you're just saying things being broken down, it's not quite good enough. You could have said, high hydrolyzing reactions, that sort of thing. But digestion is the title. It says main function. And the main function for D is absorption. Absorption. And so products of digestion being absorbed. What we're not absorbing there is water, because that would be largely in the large intestine. It's absorbing the products of digestion. And then we've got a little calculation. Chance of passing a gene for antibiotic resistance from one bacteria to another is 1 in 10 billion. And the gut contains 10,000 billion. Estimate how many might receive the gene. Okay, so he wants to go, how many 10 billions are there in 10,000 billion? So, hang on. How many 10, I'm just going to put B for billion, then you don't get that confused. How many tens are there in 10,000? How many tens are there in 10,000? And there are, of course, 1,000 of them. So that's our answer. So we don't actually need to reach for our calculators there at all. Some scientists feel that these results on antibiotic resistance are a cause for concern. Suggest one reason for this. Well, if we've got these bacteria passing around genes for antibiotic resistance, well, it might be alright most of the time if these bacteria are harmless bacteria in the gut. So most of the gut bacteria are generally harmless. But it might be a cause for concern if a harmful bacterium gets in and you take some antibiotics and it's resistant to them. So it's the chance that this gene might transfer to a harmful bacteria, or pathogenic is the right word there to say kind of harmful, or anyone that causes diseases. So this antibiotic gene may transfer to a pathogenic or disease causing bacterium, and that could be the problem there. But the important thing is these are pathogenic, and that's 8 marks on digestion.